Hello students, so let us continue. Let us discuss the next method to determine the transport number of an ion using next method that we will call moving boundary method. Moving boundary method. Moving boundary method. Now, as the first one I discussed, this is also a method to determine the transport number of a particular ion. So, in this particular method, what's the experimental setup? That now you have to understand. Here, now it consists of a cell which now vertically arranged tube. Okay, you can draw now nicely. It will be a this will be a thick portion there. No, here you will see a thin portion and like this where no two electrodes will be connected. Here now a inert electrode is connected that we can call a platinum electrode. Inert platinum electrode is connected. Inert platinum electrode is connected, which will act as a cathode because it's connected to the negative terminal of the battery. If negative terminal connected means that particular electrode become cathode, right? So that is a cathode, and a cell is there. Then you can imagine a switch. A switch will be there. Then no a resistance. Then it's connected in series to a coulometer. No, that coulometer is helps us to find the what is the total current passed through the solution that we discussed before, right? So a coulometer is connected in series to determine the total electricity that passed through the solution. So this is coulometer. COU, right? Coulometer. Then now this is connected to this electrode. Now here we actually using a, cadmium electrode. Cadmium electrode which is now acting as cadmium electrode which is acting as here this is anode and this is cathode. This will be positive. This is cadmium electrode which is now connected to the positive terminal. So this is now anode for you. This is anode. So now here now is again is a method to determine the transport number. So here we taking an example. We want to find the transport number of H plus ion from of the HCl hydrochloric acid, and we use two types of solution. Two types of solution now we are using here. Let us discuss how to determine the transport number of H plus ion using an electrolyte solution, also using that is cadmium chloride solution. So two solution are filling here. One is HCl solution. HCl solution that we will call principal electrolyte solution. Principal electrolytes. Principal electrolytes. And another one is now cadmium chloride solution that we will call indicator electrolytes. Indicator electrolytes. So these are the two types of solution that we filling in the tube. So here now we want to find the determine the transport number of H plus ion. Okay, so the principal electrolyte is HCl and indicator electrolyte is cadmium chloride. Here now two solution will separate from each other. Where now HCl is lighter and less density, that means it will float up. So upper solution will be HCl, lower solution, the lower part will be cadmium chloride solution which is more denser. So that's the way you can see two solutions are separated from each other. Lighter solution, electrolyte solution will be up, lower lighter solution will be up, and denser electrolyte solution will be down. So in this portion you will see cadmium chloride portion and the upper portion will be HCl solution. That's the way now it will exist in the in this tube. In this glass tube, you can observe like that. And what's the now? What is the criteria that is needed for indicator electrolyte? Indicator electrolyte generally we select based on the it's based on the principal electrolyte where it should have a common anion, like here Cl minus is the anion for HCl, and here also Cl minus is the anion. So that's one of the criteria. It should contain a common anion. Then now, if you want to determine the transport number of H plus ion, then now the CD2 plus here, cadmium 2 plus ion, which is a cation, should move slower compared to the transport number of the ion that we want to determine. Here we want to determine H plus ion, which is smaller, so now it will move faster compared to CD2 plus ion. So that criteria should be maintained. CD2 plus ion should move slower. We know CD2 plus have higher size, which means now it move slower compared to H plus ion. Based on that, now we usually select the indicator electrolyte. So upper solution HCl and lower solution will be cadmium chloride. So now let us discuss now how we are determining the transport number of H plus ion using moving boundary method. Here imagine two solutions are separated. So here somewhere here now imagine a boundary, let it be a dash, which actually separate the two solutions. So this portion HCl, this portion cadmium chloride. Now, once the electricity, this is the case now, this is the boundary before electrolytes. This is now boundary before electrolytes. Boundary before electrolysis. Boundary before electrolysis. Now imagine now once the electricity is passed through the solution, once now the electrolysis is carried out, what will happen? You can see the negatively charged Cl minus, negatively charged Cl minus will be there in the solution. That will move to the positive electrode. That's move towards the anode. At the same time, H plus ion solution will be there in the solution. That will move to the cathode, because cathode is negative terminal, and Cd2 plus ion. Cd2 plus ion which will be there in the solution also move towards the cathode. So that's an observation. That's something happening inside the cell during the electrolysis. The positively charged H plus ion and Cd2 plus ion move towards the cathode, and Cl minus ion move towards the anode. So that's the change you'll observe. So here now, since H plus ion is smaller, that move faster, and it will move first compared to Cd2 plus ion, because now Cd2 plus ion is higher in size and it is present in the lower portion. So there we can understand that now once the electrolysis is carried out, we can understand a boundary between the two solution has been shifted after the electrolysis. Let me represent the boundary. Let me here. Let it be BB dash. BB dash is the boundary that is shifted. This is the boundary that we are talking about. Boundary, it was AA dash before electrolysis. Now it's shifted to BB dash after electrolysis, because the movement of ions that is taking place in the during the electrolysis. So that boundary, how much the boundary is moved, that part now we are utilizing to calculate the transport number. So let us discuss one by one. Here now, let the length of the boundary that is shifted. It was A dash and B dash. Let it be L is the length between these two boundaries. And the area covered, let it be A is the area that is covered between the two boundaries. Having got that value, let us now discuss step by step. First one, the let L be the length covered. Let L be the length covered, and A be the area. A be the area of cross section. A is the area and L is the length. L is the L is the length of the boundary that is covered. Let it be in centimeter, and A is the area that is now covered, area of that boundary portion. Area, let it be A centimeter square. Then now the volume between these two boundary will be length into area. That will be L into A centimeter cube. So that is the volume covered between the two boundary. Now let us discuss now. Let C be the constant normality. Let's see be the normality of acid that we used. Okay, let it see gram per equivalent, that we represent gram per equivalent. Let's see with the normality of acid that we use in gram per equivalent. So now let us discuss what is the number of gram equivalent of H plus ion that move towards the cathode. We know some H plus ion are moving towards the cathode. So let us discuss the number of gram equivalent of H plus ion that move towards the cathode. That we can determine by just V will be the volume, C is the gram equivalent divided by 1000, because it's given in centimeter cube. We know 1000 centimeter cube is 1 liter. So we want to convert it into liter. So Vc divided by 1000 will give you the number of gram equivalent of H plus ion that move towards the cathode. So that's a important step here. Then now next method, next step let me clean this. Next step, the 1 gram equivalent of an electrolyte always carry 1 farad of electricity. That's a very important step that you can remember. Always 1 gram of any equivalent, 1 gram of any electrolyte carries 1 farad of electricity. So let us discuss the quantity of electricity. The quantity, the quantity of electricity quantity of electricity carried by H plus ion, carried by H plus ion, which will be equal to the same Vc divided by 1000 Fahrenheit. So this will be the quantity of electricity. We know some concentration of H plus ion are moving towards the cathode. So we want to determine the electricity carried by the H plus ion which is moving towards the cathode. So that will be the quantity of electricity carried by H plus ion, Vc divided by 1000. Now we can understand what is the total. Let Q is the total electricity passed through the solution. Total electricity passed through the solution. That we can easily determine now using coulometer, because the amount of substance deposited in the coulometer will be always proportional to the amount of electricity passing through it. So total quantity of electricity passed through the solution, let it be Q. Then now you can easily determine the transport number of H plus ion. Now having all these values, you can find the transport number of then the transport number of H plus ion will be Vc divided by thousands divided by Q. Q is the total current. Vc divided by 1000 will give you the amount of current that carried by the H plus ion. So if you divide these two, you will get the fractional current carried by H plus ion. That's nothing but transport number of H plus ion. So Vc divided by 1000 divided by Q is nothing but Vc divided by 1000 Q. So this is our final equation to determine the transport number of H plus ion using moving boundary methods. So let us discuss one problem that will make things easier. So in a moving boundary experiment, 0.1 normal solution used the boundary moved 4.44 centimeter during 70 minutes when a current of 5.20 milliampere was used. The cross-sectional area of the tube is 0.25 centimeter cube. Cross-sectional area means it should be centimeter square, right? So it's 0.25 centimeter square. Calculate the transport number of K plus ion. That's the question. You are asked to find the transport number of K plus ion. The equation that we already know is Vc divided by 1000 Q is the equation. So let us now find out what is each terms. V is the volume covered. For that, now the length is given. What's the length of boundary that is covered is 4.44 centimeter, right? 4.44 centimeter into what's the area that is covered? That is 0.25 centimeter square. 0.25 centimeter square. This is the area. So multiplying these two, you will get the volume that is covered. That is equal to let it be. Now finally you can now calculate 0. This will be something into centimeter cube. Okay, keep that in mind. Centimeter into centimeter square will be centimeter cube. That is the volume. So what about C? C concentration of the acid. That also given, it is 0.1 normal, which means no gram per equivalent. Sorry, it is the normality equivalent per liter. That will be the unit of this normality, or you can express equivalent per decimeter cube. Either you can express equivalent per liter or equivalent per decimeter cube. That's a C value that is given. Then now what about Q? Q you have to find. Q is the total amount of electricity that passes through the solution. Q, we know Q is equal to IT. That's the equation. I is the current, T is the time. So let us now substitute. I is given 5.20 milliampere. 5.20 milliampere means no into 10 raised to minus 3 ampere. Please no convert milliampere into ampere by multiplying 10 raised to minus 3. Then now this time is also given, how much how long it's passed. It is 70 minutes. Remember, minutes should be converted into seconds. So this will give you the amount of electricity that passed through the solution. And now remember, you have to convert it into farad. We know 96500 coulomb will be equal to 1 farad. So whatever this is we obtain in coulomb. So whatever the electricity that you obtain divided by 1 farad, that is 96500, will convert the amount of electricity into the unit farad. So for to getting into farad, we now divided by 96500. Now let us know everything is now is done. Now let us substitute. Transport number of K plus is equal to V into C divided by 1000 Q. So V into C. So 4.44 into 0.25 into 0.1 divided by 1000 into what is Q, 5.20 into 10 raised to minus 3 into 70 into 60. So this is 9650 at the bottom, means during the calculation it will come up. So transport number of K plus, let us substitute. It will be equal to 4.44 into 0.25 into 9600, that is come up 96500 divided by, that is 1000 Q. 1000 means 10 raised to 3, right? 10 raised to 3 into this Q part, 5.20 into 10 raised to minus 3 into 70 into 60. 70 into 60. So substitute this R value, you're going to get the transport number of K plus ion in farad. So do the calculation, you will get a transport number of K plus ion will be 0.4904 will be the transport number. So that will give you transport number of K plus. If you want to know the transport number of the anion, just now 1 minus T K plus will give you the transport number of anion as well. T plus T minus will be always equal to 1. Keep that in mind. So this is the equation to find the transport number of a ion using movie boundary method. Vc divided by 1000 Q, where V is the total volume covered in that boundary and C is the concentration of the electrolyte that we want to find. So let us see, the concentration should be in equivalent. The norm should be normality. So equivalent per liter, and Q is the total electricity passed through the solution. Q, for finding Q, you can either use Q is equal to IT, which is now current into time. So that equation you can use to find the total current, based on the question. Or now Q is nothing but it's the total current passed through the solution. So now that indirectly will give you the amount of substance that is deposited at the coulometer. So now that you can equate if needed. So that's the way you can find the transport number of an ion using moving boundary method. So next is no application of conductance measurement. Now here in this whole chapter we talking about conductance, right? How what is the how we can measure the conductance, how it varies for strong and weak electrolytes, different theories like the vehicle theories. So many things we discussed, right? Now let us think about the application of conductance measurement. Now here now first application which we already discussed before as based on Kohlrausch's law. If you can measure the conductance of an electrolyte, now there are so many applications are there. First let us rewind based on Kohlrausch's law. We discussed that already, the calculation of limiting molar conductivity of a weak electrolyte. That's no for a weak electrolyte, now you can still find the molar conductivity at infinite dilution based on conductance measurement that we already discussed. Now second point, calculation of degree of dissociation of weak electrolyte, lambda m divided by lambda m 0, which will give you alpha, that is the degree of dissociation. That also we discussed before. So that's another now application. We talk about now application of conductance measurement. So based on Kohlrausch's law, these are the applications. Determine the solubility and solubility product of sparingly soluble salt. Yes, that also we discussed. Please now go through that portion to understand. And determine the ionic product of water. So these are the four important applications of measurement of conductance. So now based on Kohlrausch's law, that we discussed it before, so I'm not repeating. So next now another application of conductance measurement is the conductometric titration. That's very important because nowadays now we for finding the end point of a titration, and we usually go through the conductometric titration. Previously now we have to take two solution. One will be unknown solution, one will be a non solution. We have to titrate between these two, and you have to accurately find the end point, and then by using the calculation you have to determine the amount of substance that present in the unknown solution. So whole procedure was there. Now based thanks to conductometric titration, the titration become much more easier, and that is one of the major applications of now conductance measurement that we will discuss. Conductometric titration, okay, that we will discuss in the next class. It's a very important session. So thanks for listening. Let us wind up.